Hello, good morning to all of you. So let us start the class. And can you hear me?
Yes, sir.
Yes, sir.
Okay. So today we'll have the last class of this course. And so first, what we'll discuss the remaining part of central force problem, particularly the stability of circular orbit, and then little bit discussion on Kepler's problem. After that, we'll have some time for if you have any doubts, any things that we'll discuss. Regarding the assignment, let me tell you, I'll be there in the afternoon in my office today from 2:30 to 5 o'clock. So, those who are in campus, please submit your assignment that time. Uh, those who are not in the campus and not attending the laboratory classes can write me to the email address which I have given, or in which you have given the exam, mid-sem exam, that is bpmonlinec@gmail.com. So submit, first you write why you are not in the campus, and then you submit your assignment there. I'll check your attendance from your laboratory book also, that who are present, and but I want everybody present in the campus should submit their assignment by person and hard copy. Okay, so any question about the assignment? And don't call me for the assignment queries. If you have, just follow the class. I have given all instruction in the class, and still you people are calling early morning, late night for where to submit, when to submit, how will submit. Every instruction is given in the class. And those
Sir,
who are those who are calling, basically they are not attending the class, or they are not listening the class. Tell me.
so can you repeat the timing you will be in the campus or the office? There was some network issue. It got cut.
2:30 in the afternoon, 2:30 to 5 o'clock, I'll be in my office. So that time you submit it. Okay, so we'll discuss the stability of circular orbit. Uh, and after that, let me get my pencil. Where is the pencil? So I said, if you remember that effective potential analysis, that where if you have the energy equal to the minimum of the effective potential, then we can have possibility of a circular orbit, right? So that we have to analyze carefully, that where exactly where we have the minima. Okay, so for example, if you have a, say, effective potential of this kind, so this is the minima, this point is the minima point, so this is the so total energy of the particle will be equal to minima of the u effective. Then we can have a circular orbit, that we have discussed. This will be have a this energy, you can have a elliptic orbit, possibly elliptic orbit. uh, it may not have a closed orbit, that also I argue, but depending on the potential it depends. So in case of stability of the circular orbit, possibility of circular orbit when total energy is the minimum of the u effective, this is possibility. Now whether this is actual minima, because you are how to find a minima? Suppose minima u effective, so we first u effective with respect to r, and r equal to r0 is the minima, will be 0 at the minima. But this is also condition for maxima. So this is minima plus maxima. But for circular orbit, it has to be true minima. Suppose if I have a potential like this, then this is not a minima, this is a maxima. So there is a it is possible that there you may not have a circular orbit, stable circular orbit. It may have some temporarily circular orbit, but so you have to find true minima. So true minima, you have to put another additional constant d2. You have to check double derivative at this point r equal to r0. This point, that point where we have r0 minima, it should be greater than 0. So that should be, the double derivative should be positive. Positive means you have the curvature. I don't know whether you have heard or not. Curvature should be positive. Anyhow, so this is the condition for true minima. So stable circular orbit, you have to put this condition as well as this condition. Okay, you have to check this condition. Okay, so that is the true minima case. But now let us consider an example to illustrate this point. Suppose I have a potential central force F, not potential, central force Fr is alpha r to the power n. N is integer, positive integer. Okay, 1, 2, 3. And then for what value? For what value of n? What value of n we can have a stable circular orbit? Okay. So that okay. So first thing is that first step is have to find effective potential. So effective U effective will be UR plus L square 2 mu R square, right? So this you have to find. So you have to find this potential. Force is given. So UR will be minus FR dr. This you know this formula. So then you can FR is minus of plus, then alpha r to the power n dr. So if you integrate this, this will be minus n r to the power n plus 1, right? Alpha is of course there. No, I'm sorry. The integration is not. I'm sorry. This. So this will be minus alpha, then n plus 1 r to the power n plus 1, right? This is the integration. I did differentiation. No. Just I'm doing mistake. R to the power minus n. So r to the power minus n. So if you will have minus n plus, sorry, I'm doing the mistake. So let me erase. So let us integrate this. So minus plus. So this will be plus. Sorry. So plus alpha. Then r to the power minus n. So r to the power minus n plus 1 divided by minus n plus 1, right? So this will be the result of integration. So your effective potential is basically U effective will be alpha by 1 minus n and r to the power n minus 1. So this is your plus L square to mu r square. So this is your L is constant, that angular momentum. So first you have to first derivative and find which point are possible for, say, let us r equal to r0 is the extremum position. So then del at r equal to r0 should be 0, right? So if I differentiate alpha 1 minus n, then r to the power 1 minus n, so it will be 1 minus n, then r to the power n, this differentiation, right? R to the power n minus 1 plus 1, this you are differentiating, so 1 minus n, then r to the power differentiate means r to the power minus n, so that, okay, this. and this will be L square by 2 mu, L square by 2 mu, and then R square minus 2, so 2 by R cube. Okay, and that at the point R0 should be 0. So if you simplify, let us do this. So first term will be, this will get cancelled, and alpha by minus plus, there will be yeah, so it will be minus alpha R0 to the power n, and this side you will have there is a sign mistake I did. Let me check. When you differentiate, you effective differentiate r to the power minus r to the power n minus 1. Okay, sorry. So you are differentiating r to the power n minus 1. So it will be n minus 1 times r to the power. What nonsense. Just a moment. I'm a little bit in hurry. So okay. So you have to differentiate r to the power minus n plus 1. So if I differentiate it, it will be 1 minus n power into r to the power minus n. Okay. So 1 minus 1, and then why this minus is coming? This minus will not come, no? So that is the problem. Okay. So this will be plus. I had alpha 1 minus n, so that is mistake I did. Okay, so it will be alpha by plus alpha by r0, and then it 2 will get cancelled. L square mu r0 cube should be equal to 0. So this is the first condition to have a minima or maxima. So let me write alpha by r0 to the power n should be equal to L square mu r0 cube. Right. So this is the condition. R0 should be such. I'm not finding a solution because this will be used later. Now for stability, you have to find double derivative. So d2 u effective d r square at r equal to r0 you have to calculate. So if you calculate and use this condition, you will get, let me differentiate where is my so this is alpha. Du effective dr was alpha by alpha by r to the power n, and then you had minus L square mu r cube. So if you differentiate twice, second times, then it will be alpha differentiating minus n, so it will be alpha minus n r to the power minus n minus 1, so n plus 1, right, minus alpha n, this is fine. And then this term, second term, when you differentiate, minus then L square mu r cube differentiate, so minus plus 3 r to the power 4. So at r equal to r0 should be 0, greater than, so it has to be greater than now. Okay, so now if I substitute r equal to, so alpha n minus r0 to the power n plus 1 plus, because now it is because of derivative, 3L square, and mu r0 4 should be greater than 0. So if I take what I'll do, if you take alpha by r0 Okay, now we have to use this condition. So alpha square mu R0 cube. So so this condition alpha square mu R0 cube is same as alpha by R0 to the power n. So I'll use this in the second term. So alpha n then R0 n plus 1, and then this condition if I use 3 L square 3 by R0 will be there. So it will be R0 square, no, R0 to the power n. So R0 to the power n plus 1, and there will be alpha. Got it? L square mu R0 cube. I substitute. So 1 R0, so that R0 will be n plus 1 because this is alpha by R0. So this I substitute. The condition, this condition I substitute here, you will get this. Now you take common alpha by R0 to the power n plus 1. If you take common, so it will have 3 minus n. Right? This is 3 and this is minus n. That should be greater than 0. So 3 should be greater than n. So this is the condition for stable circular orbit. Okay. So this problem, but you have to analyze your, depending on that situation, you can given different problem. What you have to do, you have to put this condition. So this is the condition for stable circular orbit, and of course this condition is there always there. Okay. This is now 24 minutes and somebody wants to enter in the class. No way. You just go to hell. Okay. So so this is any question about this? Okay. So now next the remaining topic is that we will discuss little bit about the Kepler's problem. This problem you must have studied in your mechanics class. I don't know BHO syllabus, I have not. So Kepler's problem, U R is your minus alpha by R. This is your potential with alpha greater than 0. Okay. So FR we have to find orbit equation and see that what will be the orbit. So it will be alpha square. So minus and then there is a differentiation, so that will create this alpha R square equal to this will be minus. Okay. So this alpha, so orbit equation is if you remember yesterday in last class, d2 small u d theta square. Orbit equation was u equal to mu f of 1 over u L square u square. So this was the orbit equation. Now u is 1 over r. Okay. So your f is basically minus alpha u square, right? So f equal to mu then minus alpha u square and then L square u square. So for orbit equation, if you want to find for Kepler's, so u square get cancelled, and then you have d2u d theta square plus u equal to minus alpha mu by L square. Minus or plus, I see plus. Why? There was this is minus. This term is orbit equation is minus. Orbit
Yes.
there was a minus in the orbit equation.
Yes, sir.
Yeah, I think so. This orbit equation will have a minus. So this is actually minus, and this minus will be plus. So okay, so this is orbit equation, and this is very simple equation. Right hand side is constant. So I can define my u prime equal to u minus alpha mu by L square Let me see. Yeah. So then your d2 u prime d theta square will be same as du d theta prime, d2 d theta square. Okay, this theta is same. U only u and u prime are changing. So u prime. So this is same because this is constant. So I take it. And this when I take minus, then this will be. So this equation, if I substitute, it will be d2 u prime d theta square plus u prime equal to 0. So by this substitution, you will get this equation, and this is very simple to find a solution of this equation, this very familiar equation, and this equation generally can be written as u prime equal to say some constant b and cos theta minus theta 0. It is second order equation, so there will be two integration constant. One is b, and in this form you can write. One can write in terms of exponential, one can write in terms of sine cos combination, but this is a solution. And then you have to boundary condition you have to use. So u prime, is u minus mu alpha by L square equal to, so u equal to this plus b cos theta minus theta 0. But now you have to find this constant from your initial condition. So your r 1 over r, let me write, and you can write m alpha L square. If I take a common outside this common, so it will be 1 plus, and now you will have say e cos theta minus theta 0. So I can say that my e will be b L square alpha mu, right? So this equation is kind of familiar equation, and for different orbits depending on the value of e, but that value of e depends on an integration constant b, and that b one has to find from the initial condition, because this is the general solution of that potential. Now initial condition you have, from initial condition or boundary condition you have to find this theta 0 and b. Then only you able to find that what will be this this is for the conical things, that eccentricity. So depending on this eccentricity, you will find the orbit will be parabolic, hyperabolic, ellipse, circle, etc. Okay, but this same equation you can obtain. You remember that when we talk about fast integral of motion, the same equation also you can find from that equation. We wrote this equation d theta equal to theta, d theta equation I wrote LDR, if you remember, mu r square root over 2 by mu e minus potential minus L square 2 mu r square. So this integration, so by integrating this, you can find theta equal to r0 to r integration dr by this. You can write r square, and you can simplify bringing mu inside. You can find mu, if you bring it inside, then there will be, okay, so 2 mu e 2, then there will be 1 mu, this mu go inside will be mu square, so 1 mu will get cancelled, 2 mu e by L square minus 2 mu u by L square minus 1 over r square. So this integration, and this integration you can perform, and then this will be the constant of integration theta 0. So I'm not going to discuss you how you will able to find this, but this is a straightforward integration you can do in terms of cos hyperbolic, etc., and all these things. So from there you can find your this result. Let me write the directly from the result. If you solve in this fashion, you will find that 1 over r will be mu alpha L square times 1 plus root over 1 plus 2e L square mu alpha square times cos theta minus theta 0. So in this approach, if you perform this integration, then one advantage is that you can find basically the another constant. So only you have only one theta 0 constant, and you can find okay, so you can find, and you can comparing with this will be basically, if you compare with the earlier equation, this will be your E. So E is basically root over 1 plus 2 E L square by mu alpha square. Okay, so now if you can easily see that E greater than 0, so E greater than 1, right? So it will give you the hyperbola. Similarly, if E equal to 0, small e will be 1. So this will be parabola. Okay. E less than 0, negative. So this term will be negative. So it will be less than 1. So small e should be less than 1. So it will be ellipse. And E equal to this, E equal to say minus of mu alpha square by 2 L square. That means this term equal to 0. So this will be 0, and that condition will be circle. Okay. So this is by from the integrating the Kepler's problem. Only thing that I have not done this integration, but this integration from your 12th class knowledge, you can find this integration and get this result. So this is all about the Kepler's problem, and similar analysis you can do for whatever problem you can solve in your using your those who are integrable, you can solve and you can analyze their exact nature of the curve. Effective potential plot, when we do the plot, we have this for Kepler's problem. So from here, if you have this energy where E greater than 0, so for Kepler's problem it will be hyperbola. Now we can say, now E is 0, this line E is 0, so it will be parabola. Okay, so this line will give you the E equal to 1. Similarly, this line where E is negative but not beyond this, then negative but less than greater than this negative value, so then you will have ellipse. But tentatively we also find that it will be ellipse, or it may be some close but not, and this is the energy, we found for this energy, it will be circle, and you can check if this circle will be stable. You can check yourself double derivative and this. So this is the conclusion of your syllabus. Now tell me if you have any question, queries, etc. On this topic first. Then we'll discuss your questions if you have any from other topics. Okay. Just let me know your questions. Then I'll discuss general discussion on the whole course, because today is the last class. Any question?
Sir, can you please explain canonical transformation if you can, like the basics?
Okay. Okay. So let me explain that. Uh, so it was taught in the class, right, by Dr. Kista. So let me know quickly what he has taught. I mean, just topic wise outline.
Sir, Krista sir taught us four cases, so I was confused. Like he was telling that we have to use this type of canonical transformation when this thing occurs. So I was not able to understand that part.
No, where you have to no, I didn't understand your statement. I can just repeat the statement. Shruti, tell me again what was your statement.
Sir, Krista sir told us four types of canonical
But
transformation. Like
that is coming later, no? Four types that will come later. Okay, anyhow, and then the fourth type of generating functional he has discussed, and okay, so first thing is that let me spend some time because he asked that, and it is an important topic. So let me discuss, at least spend 10 minutes on canonical transformation. So first thing, you should know a clear definition of this. This we open when the usual closed book exam we used to ask almost every year. What is the what are the canonical transformation? So that you should have. So let me define it first, and then I'll eliminate the mathematics, but I'll discuss what is the meaning of that. So canonical first transformation means you have to know canonical variables. So first you must have studied Hamiltonian, and you know what are the canonical variables. Canonical variables means those are coordinate and its corresponding momenta. They are canonically conjugate because if you know that q dot is minus q dot is del h del p, and you have p dot is del h del q. So this not because of that, but if you take a Poisson bracket of q and p with respect to q and p, then it is always 1. Poisson bracket of this. So any quantities whose Poisson bracket is 1 and among themselves Poisson bracket is 0, then those variables are known as canonical variables, canonically conjugate. Okay, so q and p are known as canonically conjugate variable. Exactly in quantum mechanics also, x px commutator is IH cut, and xx commutator. So they are canonical variables conjugate to each other. X is conjugate to momentum x. So first canonical variables. So now canonical transformation is a transformation from one set of, so this is my set of canonical variables, and let me define it is old set to a new set. So new set. I can define, right? I can define a old set, this is a new set. And this will be here Hamiltonian will be H, suppose, and here Hamiltonian is H prime, suppose. So this, let me write Q I P I Hamiltonian, and this is capital Q I P I. So canonical, this transformation from old set of canonical variables to a new set of canonical variables will be called canonical if it means this transformation, or if the transformation preserves the canonical equations. Canonical equation means these equations. These are equations are called canonical equation. That means it preserves mean what? Preserve means if your Qi dot is del H del Pi minus and plus Pi dot is del H del Qi, then if it is a transformation is canonical, then Qi dot minus should be del H prime del Pi and Pi dot should be del H prime del Qi. If this holds under this transformation, then this transformation is called canonical transformation. Okay, definition is clear. So to check, then you have to use this transformation and use the Hamiltonian from H to H prime. Then you find that to check a transformation is canonical or not, there are two ways. One is that you can check that, oh, I may forget, no? Just a moment. So, so F was QQ. So DQI PI minus capital PI DQI is, for case of time independent, is exact differentiation, sum over all I. So this condition you must have proved. Not only this, there will be 4 such condition, total 4 such condition with this kind of. So 4 condition. So if to check a transformation is canonical or not, you know the old variable, you know the new variable, then you calculate this and show that this is the exact. Exact means it can be written D of some F, where F is function of old and new variables kind of thing. So this, then exact differentiation, you know something is called exact differentiation, that mathematical terms you know. So that similarly there are other condition also. For example, let me recall, I was not prepared now. So this is F1 corresponding, there are 4 generating functions, so it is Q, Q and T, right? So F2 was Q, P and T, I think. I don't remember which one is F2. So if that is that, in that case, again there will be another condition like Q. So Pi d Qi plus or minus, you have to check. Here it is P, so it will be Qi d Pi. This also will be exact. So there will be 4 type. You just check in the book, you can find there are 4 type of things. So this is the way 1. Second way is that prove this theorem that canonical transformation preserves the fundamental Poisson bracket. What are the fundamental Poisson? So if I Qi and Pi, if they are dynamical variables, fundamental Poisson bracket is Qi Qj is 0 equal to Pi Pj with respect to Q and P. This is our old variables. I am not bringing any new variable. So they are called fundamental Poisson bracket. Qi Pj Qp equal to delta Ij. So these are called fundamental Poisson bracket. So if the fundamental Poisson bracket preserves, then we call this transformation is canonical. This is a theorem. It can be proved. I think you should have proved in the class, but otherwise you should learn it in any standard book. This is. So to show a canonical transformation, but this is with respect to own variables. Now to show a canonical transformation, you have to see whether it preserve under canonical transformation or not. So Qi, Qj with respect to new variables also should be 0, should be Pi, Pj with respect to new variable. And Qi Pj with respect to new variables now should be delta ij or vice versa. So small q pi to capital Q capital Pi transformation will be canonical if the Poisson bracket, I am calculating this Poisson bracket now fundamental Poisson bracket but with respect to new variable. Vice versa means same proof I can do but Qi Qj Poisson bracket of old variable new variables fundamental Poisson bracket with respect to old variable should be 0 and should be Pi Pj Poisson bracket with respect to old. So fundamental Poisson bracket of the new variables with respect to old or fundamental Poisson bracket of the old variables with new variable with respect to new variables. So this you have to check. Should be delta h. So this you have to. So this is the alternative way of doing this Poisson bracket, checking canonical transformation. Now, why we study canonical transformation? Why we study canonical transformation? So suppose I have a Hamiltonian. If you look at in your assignment, there was some Hamiltonian which is little bit difficult, like 1 over q square p to the power 4 or kind of thing, right? So suppose this Hamiltonian H is for which the implies difficult canonical equation. Okay. So I have a system H. I want to find a solution, but these equations are difficult. Canonical equations are difficult. So what I do, I make a canonical transformation, go to an H prime and then find canonical equation. And this equation may be simple. So this is important thing. I have a canonical I design a canonical transformation to make the Hamiltonian simple, such that this equation is simple. I find the solution. So solution was found. Then I use inverse canonical transformation to go back to this solution. So our aim is to find solution of H Hamiltonian. I can go directly here, but this method, this path is difficult. Instead of that, what I do, I make a canonical transformation, make a simpler Hamiltonian, but this is also not that easy, but it is possible. Sometimes this solution may not be possible. Then you find H prime, equation simple, find a solution, take inverse transformation. This is a longer route, but you can reach there. But sometimes it may be possible that these equations are so difficult, you cannot find the analytical solution. So that is the use of canonical transformation. In your assignment, one Hamiltonian is given. I don't know in which group it belongs. That Hamiltonian is basically, let me know if I have the PDF file in front of me.
$52 question.
But do you remember that? I don't.
51.
Yeah, maybe I have this question. Let's see. Yeah, I can. So you know 52 means you know the Hamiltonian, right?
51. It's 51.
So I got the set. Yeah. So now you can do this. What I said, the motivation H was in 51.
Yes, sir. It's like Laplace, what we did. It's similar to that. Like we change
Laplace.
then and then inverse. That
Yeah,
one
yeah,
should be.
yeah. And every transformation is that. So this Hamiltonian, first you try to find the canonical equation, and you'll find that those are not simple. But then I have asked that. I have not asked, but this Hamiltonian can be converted to a simple harmonic oscillator Hamiltonian. Simple harmonic oscillator Hamiltonian means p square plus some constant q square. This type of Hamiltonian, which solution is known to us. It's very easy to find solution. So if I find a canonical transformation to find a solution of this Hamiltonian, direct method is difficult, but I make a canonical transformation to make it a simple harmonic oscillator, then it will be easier. So this is the. Now in the canonical transformation, there are 4 type of generating functional. Let me write Q T. Then there will be I think Q P T. Then F3 will be P Q T. I don't know, but this check the book. F2, F1, F3. You can design anything, but PP. So, and there are some differential equation to generate differential equation this to find canonical transformation. Now another type of question generally we ask in the exam, that find the generating functional. Given a canonical transformation, you have to find a generating functional. If I have some example, let me see. Okay, in 46, let us see in the 46, it is given that, or maybe I can, okay, 46, I don't know whether I can immediately do or answer or not. Q is Q to the power alpha, capital Q cos beta P. If I cannot do, I can at least tell you the technique. P is Q square sine beta P. Suppose this transformation for, no, this should be alpha also, or I don't know. First you have to find for which value of alpha and beta this will be canonical, and then okay, maybe 47. So I don't know for which value. I think alpha equal to 2 or alpha equal to half. I don't know, but so let us take a canonical transformation. 47 3. This is a canonical. Q equal to P square plus Q square, and small p equal to half tan inverse P by Q. Suppose I need to find a generating functional F1. Okay, suppose. So Q, Q and T. Okay, it can be multivariable. I am just simplicity taking one variable. Okay, so equation, what are the equation? You know, del F1 del Q was your P, right? And del F1 del Q is your minus capital P. So if you have to find your F1, what you have to do? You have to, suppose I want to find from this relation. So F1 will be my P dq integration, right? Or if I want to find from here, F1 will be minus capital P d capital Q, this integration. And this thing you have to substitute from these relations. Okay. So suppose which one will be better? Capital P. Suppose this capital P, this will be better. So let me try to find. So basically the mathematical difficulties is that you have to find this integration. But careful, here these two variables are independent. When I write Q and Q, these are two variables are independent. Rest of the variable can depend each other. So you have to be very careful. So whatever you write here expression, it will be preferable if you write in terms of Q, because Q then that can be taken out of integration. This integration is with respect to capital Q, so small q can be taken outside. This is the important thing. So let me try to proceed. So if I use this formula, so it will be where is this formula? Then I can write P by Q equal to 2 tan tan 2p tan 2p. So capital P will be Q tan 2p. But now capital P is minus Q tan 2p dq. But here I cannot do this. P cannot be taken outside. Okay, this P I cannot take outside because they depends on capital Q. So it is difficult here. Similarly, let us take P, small p. If I substitute small p is half tan inverse P by Q. So in the first relation is small p I can substitute from here half tan inverse. So half tan inverse P by Q d of Q. Here in this integration you can take this Q constant because this you are Q and Q, so they are independent variables. But I don't know if you can integrate or not, then directly you can find if you can integrate this. But now I can understand that Q and Q, where they are independent, that generating functional is easier to calculate. For example, let me show which generating functional. Q and Q are independent. P and capital Q. P and capital Q are independent. P and capital Q. So F3. So if I try to find my F3 in this problem, it is easier. So F3 is your P and Q and T. So del F3 del Q will be P. Okay. Minus plus you check. I don't remember. So F3 will be P dq. Now P you can substitute Q to P. Q tan 2P, Q tan 2P dq. Now this and these are independent, so tan 2P will be outside, so it is Q dq, which you can integrate, so it will be Q square by 2 tan 2P will be the generating function. So F3, so if first you have to find that, of course you can obtain F1, but then you have to take a relation from F3 to F1. That Legendre transformation you can do and you can find. Okay. So this, but every canonical transformation you have to find reverse. Now my F3 is this. F3 is now I found is Q square by 2 tan 2P. Now F3 relation you use, there is F3, there will be another relation F3 by P should be Q, minus or plus you check, I think minus. So it will be minus, both classes it may be minus, I don't remember. So this will be Q. So any generating functional you find using one relation, you must verify the other relation. Both the relations should be verified by this. Okay, so today time is over, and if you need before your exam, but you have to call me, you have to fix the class. I can take a tutorial class for clearing your doubts and problems in the classical mechanics. But you have to fix the discuss among yourself, at least sufficient number of 10 people at least interested with have some problems discussion, then I can take a tutorial class of problem solving. Your exam will be little bit difficult side. Problem will be in the exam, you'll find most of the problem are unseen type of. But within everything within topic, and most of the questions will be only problems. So you have to be little bit careful. Don't take loosely. And one more request, don't call me for your assignment. I think regarding assignment, everything is clear to you. If you are not in the campus, please explain why you are not in the campus in the email, and then you submit your assignment in email. But for record, I'll keep those your email that you are not in the campus. So you could not, because of this reason, you are not. So that is why you are submitting online assignment. This is for record. And if you copy in your assignment, then if I find somebody has copied, then it will be penalized for that. And your sessional marks will try to work in the first week of December, all this, and I'll tell you your sessional marks. It will be test plus home assignment plus your regularities in the class. If you are not attending the class, I have taken 5-6 days attendance, that which I have. So those who have not college, this regularities will be 0. But you will have your test, you will have your assignment. So those. Any question? Otherwise, I'll stop this class. Any question, any clarification you need, you please ask. Okay. Okay, then bye. Good luck for your exam.